Okay, thank you for coming on our Friday. Reminder, next week we won't have a class. Okay, meaning no class on, when is it, Monday? Okay. So anyway, let me briefly go over the homework that you guys did last time, because some of the concepts are related to that homework, right? So we were looking at, what if we have multiple layers of neurons? So for example, if we have one layer over here, another layer over here, right? Another layer over here. So let's say this is the actual output, right? So in your homework, remember, inside here we have a summation activation function. So very quickly, let me just quickly draw this. We'll talk about one concept so that everybody understands. Okay, so very similarly, this goes there, this goes there. Okay, and suppose this is x1, x2, this goes over here, these also go over there, right? So this was your homework, and the weights are W11. Okay, so remember our terminology was output number, comma, input number. Okay, why did we not pick the weight to be input number, comma, output number, which will seem more intuitive, right? Anybody knows why we picked this and not this?
For the matrix?
Because this allows us to convert it into a matrix equation, this will not, okay? So that we can come up with a matrix form. So this terminology was used, right? Okay, before we come to the matrix form, we were using the superscript as the layer number. So this would be 1, correct? So what will be this? W. See, if this is output 1, output 2, W21, right? And very similarly, this will be W12 of 1, and this will be W22 of 1. Okay, very quickly now let's go put the same things over here. This will be W11 of 2, W21 of 2, W12 of 2, and W22 of 2. And W11 of 3, W21 of 3, W12 of 3, W22 of 3, correct? And then we have the activations over here. Sorry, the sum over here, right? Now if we try to develop the equation for the gradient of W11 as an example, right? So if we did W11 of 1, okay, how many paths are involved over here? You'll see there's a path involved here, correct? What's the other path? From here to here, right? Is there another path?
Yes.
Okay,
Also from the top down, going down and up.
correct. So then we use a different color, top down. Okay, so basically W11 will be the sum of the gradients, or I should say sum of chain derivatives, chain of derivatives along the dotted paths. Right, so if we wrote it individually, we can come up with 4 sums over here, okay? And you can see if I added one more layer, or if I added more neurons over here, this could easily get out of hand, okay? So we developed the delta rule for this purpose. So this is called the delta rule. Okay, and again, if you go to the internet, you'll see all sorts of explanations and examples, but in my opinion, the best way to understand this is think of the delta as a partial computation in the middle of the neuron. Okay, so if this is our sum, this is our A1 of 3 as an example, S1 of 3, right? So whatever, as we are doing the back propagation, the product of the derivative of the loss function, so if there's a loss function over here, okay, so partial L over, for example, partial A1 of 3 times partial A1 of 3 divided by partial S1 of 3. So this product, which is basically the cumulative derivative up to this point, is what we will call delta 1 of 3. So, okay, and very similarly over here, delta 1 of 2. Okay, so in terms of the deltas, our whole answer becomes a lot cleaner, a lot smaller. The computations gradually build up as we work backwards in the backpropagation training algorithm, right? So let's call this delta 1 of 2. Let's call this delta 2 of 2. And very similarly, let's call this delta 1 of 1 and delta 2 of 1. Okay. So now, rather than writing this sum of 4 derivatives along the 4 paths, we can easily do step by step. So this will be our delta 1, correct? Delta 1 of 3. What will be our delta 2 of 3? Partial L over
partial
A2 of 3 times A2 of 3 over partial S2 of 3. Okay, so once we know these deltas in the middle, then the question was, how do we come up with the deltas here? So these deltas can now be computed in terms of the deltas over here. So see, so basically, let me draw a line over here. So if we wanted delta 1 of 2, you can see here's this weight involved, which is basically accumulating the delta 1 of 3, delta 1 of 2 over here, right? So first, let's accumulate up to this point. Up to this point, what will be the accumulation of deltas? It will be delta 1 of 3 times W11 of 3 plus delta 1 of, oh sorry, delta 2. Okay, did I write it wrong? This should be delta 2 of 3, correct? So this will be delta 2 of 3, and what's the weight that brings us to? W2 of 2. Okay, so that gives us up to, so that's not the delta. That is simply the accumulation up to this point before the activation function. We further have to multiply this by the derivative of the activation function. Okay, so delta 1 of 2 will be the so let's pretend it's a sigmoid. Okay, if it is a sigmoid, then this will be called 2, right? So this will be A1 of 2 times
1 minus 1 of 2.
A1 of 2 and multiplied by further this term over here, delta 1 of 3 times W1 1 of 3 plus delta 2 of 3 times W2 1 of 3. Okay, so very similarly we can compute delta 2 of 2. So I'll leave it as an exercise, or hopefully you've already done it in your homework. So whatever the delta 2, very similarly, here you'll be accumulating, let me draw like a solid blue path over here. So to compute this delta, you'll be, so first you'll compute the things over here. So for example, this will be delta 1 of 3 times, what's the weight that goes this way?
W2, W1, W1, 2 of 3.
1, 2 of 3 plus this delta 2 of 3 times W2 2 of 3. Okay, then further, what do we have to do? Multiply by
The activation function.
the derivative of the activation function. If it's a sigmoid, it will be A2 of 2 times 1 minus A2 of 2, correct? Then this will give us the delta 2 over here. So basically this value multiplied by A2 of 2, 1 minus A2 of 2 times whatever this value is, correct? So now that we have this, now we can continue with the same idea. Once again, you will first compute the sum based on the weighted deltas. So this will be like W1 1 of 2 times delta 1 of 2 plus this is W2 1 of 2 times delta 2 of 2. Then further we multiply by the activation. So now we will get W1 of 1. Same way over here, we'll get W2 of 1. Okay, so now let's go further. What will be our gradient W11 of 1? Okay, so remember, delta is basically an accumulation of all the chain of gradients up to that point, right? Or chain of partial derivatives. So then, if we take a look at the expression for S1 of 1, so over here is S1 of 1. What's the expression for S1 of 1? X1 times W11 of 1 plus X2 times W12 of 1, correct? Plus 1 times V1 of 1. So I didn't draw the bias, but correct? So W1 will be basically delta 1 of 1 multiplied by partial S1 of 1 divided by partial W11 of 1. Okay, so if you take a look at this expression, what's the partial with respect to W11 of 1?
X1.
Which is the previous value that is being fed to this network, right? So think of it this way as W1 of 1 time previous output. But in this case, there is no previous output, it's just the input. So basically, think of it as previous input, which basically means delta 1 times X1. Okay, so in general, as you will see in your next assignment, that you will implement a solution for multi-level neural networks so that we can have any number of neurons, any number of layers. How will we train that network? So once again, the strategy will be, in plain English, start computing the deltas in the last layer. So the strategy is, so that propagation algorithm. multiply the whole neural network. Okay, so compute forward pass. Meaning, in this particular example, you will store a1 of 1, a2 of 1, a1 of 2, a2 of 2, a1 of 3, a2. So based on the training data, somebody will give us x1, x2. We'll start storing whatever the actual output is here, actual output is here. Do we have to store the sums? I mean, of course, we'll be computing the sum before we compute the actual output, right? But do we need it in our back propagation? Do we need the value of the sum? If you take a look at any of these expressions, right, all we care is the actual output, not the sum value. Okay, so even though based on the input data, if somebody gave us, let's say, x1 of 0.5, x2 of, let's say, 0.3, let's pretend in the beginning w11 of 1 is 0.11, w12 of 1 is 0.35. Okay, let's pretend these are some random values. v1 of 1 is 0.05. Let's pretend this is how our first training data was, right? So in the forward pass, like I said, what we'll do is we'll compute this S1 of 1. Okay, so you'll feed in x1 of 0.5 as an example, multiplied by w1 of 1, which is 0.11 in this example, right? Then you'll feed in x2, which is 0.3, w12 of 1, which is 0.35. Okay, then 0.5 over here. So will we get some number over here? So for the S1 of 1, we'll get some number, right? Let me just pretend that comes out to be 0.28 or something. Or actually will be, all right. So let's suppose S1 of 1 comes out to be 0.28. So if we are using sigmoid as the activation function, then, okay, remember what's the sigmoid function? This is 1 over 1 plus e to the minus x, right? So what will be the value of a1 of 1 then? 1 over?
1 plus e to the minus 0.28.
E to the minus 0.28, correct? Okay, so anyway, that's what I said you need to store in some variable. So you very similarly, you'll compute, compute the A1 of 2, A2 of 2, A1 of 3, A2 of 3, right? So in our algorithm, you will go and store all of these values. Once you have stored all of these values, then we'll do the back propagation. Okay, so we'll compute the loss, for example. So our loss, for example, will be, as we had discussed, 0.5 y of I minus a of I squared. Okay, so in this case, 0 to 1. Okay, which is basically 0.5 y1 minus a1 square plus y2 minus a2 square. So y1, y2 are the expected outputs, which our training data will be deciding, correct? And what are a1, a2 of 3? Those are the actual computed outputs based on the forward pass, right? Once we have the loss, then we can go and start computing. For example, how will we compute delta 1 of 3 from it? Okay, so what is partial L over partial A1 of 3? So if you did a partial L over partial A1 of 3, what will it come out to be?
It's minus Y1 minus
A1 of 3, right? So that is not delta 1 of 3, that is partial L over. So everybody is clear, this is how we'll compute this part. Then what is partial A13 over partial S13? How will we compute this part?
Of the sigmoid.
That's the derivative of the sigmoid, which we already had said the derivative of sigmoid is A times 1 minus A. So in this example,
A1 of 3.
so delta 1 of 3 will be this value multiplied by A1 of 3
times 1 minus A1 of 3.
Okay, excellent. So this is how we already know through the forward pass what this value is. What this value is. This is our expected output, correct? So can we find this number then? Okay, so we'll be able to determine that number. Very similarly, we'll compute delta 2 of 3 based on the initial random values. So now can we go back and compute all the deltas over here, right? After all the deltas have been computed, what's our next goal? Our next goal is to find the gradient of each one of these weights. There are 4 weights over here, 4 weights over here, 4 weights over here. So now let's talk about how do we compute the gradient of each one of these weights in terms of the deltas. Okay.
Forget the biases.
And the biases, correct. So actually we need 4 and 2, 6, 18 gradients that we have to compute, right? So as we discussed, we have to compute delta W11 of 3, delta 12 of 3, delta 21 of 3, delta is missing W22 of 3, and delta B1 of 3, and delta B2 of 3. Okay, so let's briefly talk about how we'll compute this. Okay, let's focus on delta W11 of 3. Okay, so what we want to do is, the gradient W11 of 3. We want to compute it in terms of the delta. So in terms of delta. So that, because we already have computed all the delta values, if we can compute the gradient with respect to W11 in terms of this, it becomes a lot easier, right? So what should be the exact value of it? So for example, over here, if you take a look, it is connected to this neuron, where the delta 1 of 3 was produced, right? So if you take a look at this sum over here, so let's focus on this sum. What this sum, which is S1 of 3, will be equal to?
A1 of 2 times.
So A1 of 2, perfect.
Times W11
W113 plus, see this is A2 of 2.
A2 of 3. Oh yeah,
A2 of 2 times
W1, 2.
3, right? So now do a partial S1 of 3 with respect to
W113.
W.
Should the bias be in there as well?
No.
Oh, yeah.
Yes.
Yeah, there should be a bias.
Doesn't matter.
1 times B1 of 3. Okay, so if you did partial S1 of 3 over partial W1 1 of 3, what would that be?
A1 of 2.
Which is really the previous output, right? So basically, from here, what is the previous output? A1 of 2. So even though through the equation you can confirm the derivative is really the previous output, once you have confirmed it, now you can blindly start writing it. Okay, so the delta 1 1 of 3, in terms of delta, will be delta 1 of 3 multiplied by
A1 of 2.
A1 of 2. Okay, now let me ask you, can you give me the expression for, let's say, W gradient with respect to W2 2 of 2?
Delta 2.
Delta
X.
2 of 2 times A2 of 2.
See, this is coming from here, right? Delta 2 of 2 times.
A2 of 2.
What's the previous output? This one is A2. Correct. Okay. Lastly, let me ask you one more question, see if everybody feels comfortable now. How about W2 1 of 1, the gradient with respect to W2 1 of 1?
Delta 2 of 1 times X1.
Delta 2 of 1, and whatever the previous output is, which in this case is the input, X1. Okay. So to summarize, now you guys have a very, very good understanding of how neural networks are put together. It doesn't matter what's the depth of the network, meaning in terms of layers. Okay, it could be 3 layers, 10 layers, it doesn't matter. Okay, our general algorithm, like I said, would be do a forward pass as we discussed, right? Store all the actual outputs, because those are the ones that we will need as we backpropagate. Okay, as we backpropagate, then start from the loss and okay, then compute gradients in last layer. Okay, so in this example, these will be delta W11 of 3, I mean the gradient W11 of 3, gradient 1, 2 of 3. Okay, gradient W21 of 3, gradient W22 of 3, and B1 of 3, and B2 of 3. Okay, so compute the gradients in the last layer. Okay, then compute gradients in previous layer until we reach the input, and then we are done. So so this is the general form of the algorithm, right? Okay, so now let's say we were implementing some kind of a neural network with, let's say, 100 inputs. So okay, so suppose we had some kind of layer 1. Layer 2. Layer 3. Okay, so let's pretend we had like let me make it 1,000 inputs. And suppose over here we had 100 neurons. Here we had 50 neurons. And in the output layer, so here's our 10 outputs. So we were solving a 10 class problem. Okay, so we have 10 neurons. Okay, so one of these 10 neurons will have an output of 1 if it belongs to that particular class. So let's pretend this is a 10 class problem. So that's why the number of output neurons is 10, right? So let's try to estimate how many gradients we'll need to compute. Okay, so number of model parameters, which is same as number of gradients that we need to create. Okay, essentially in a neural network, these are the weights and biases. Okay, so in terms of the weights and biases, how many weights will be involved? See, these 1,000 will go to each one of these 100 neurons. So if there's a neuron over here, you can see all these 1,000 inputs become the input to this neuron, right? So 100,000 plus 100 biases. So this will be basically 100,000 plus 100 will be the number of parameters. These are the biases. And these are the weights in the first layer. Okay, now let's go to the next layer. Each one of these 100 will be connected to each one of these 50 neurons. So it will be 100 by 50, which is 5,000 plus 50. Okay, so then we add this, and lastly, each one of these 50 will go through these 10 plus 10. Okay, in the first assignment, when you were doing a simple, 2-neuron classification, or you had a single neuron, sorry. You had a single neuron with 2 inputs, right? There were 3 model parameters, so you came up with 3 derivatives. It was easy. When you wrote the code, you wrote it, for the 3 variables explicitly. But imagine you won't be writing, 100,000 different variables one by one. Even if you created an array of these, it will still become tricky. Okay, so the best approach that we follow in creating deep networks these days is we do everything in terms of matrices. Okay. So even though the individual things that we listed were important in understanding the algorithm, but once we go to the matrix form, then everything will become